Let's see an example of computing the associated matrix. The example will be in computing the associated matrix of the axial symmetry that we already seen in previous lectures. Consider first the same example of lecture 9.3, axial symmetry SL about a line L in R squared. In order to find the matrix A, SL, Vj, and Wi, that is the associated matrix of the homomorphism SL with respect of the basis Vj of the domain and Wi of the codomain, we need to choose the basis V1, V2 of R squared and W1, W2 of R squared codomain. We have previously remarked that choosing randomly bases, chances are that the computations will be exceedingly complicated. See lecture 9.3. Hence, we let V1 and V2 to be the clever bases that we found in this lecture, i.e. the one on which SL acts understandably. You remember in that lecture V1 was chosen to be a vector in the axis L and W2 a vector perpendicular to V1. The choice of W1 and W2, since SL of V1 is V1 itself because V1 is a vector in the axis, and SL of V2 is negative V2. While this has been proven in lecture 9.3, a clever choice of basis for W is to let W1 and W2 be equal to the respective bases of the domain. This is because you see the images that are so this V1 lives in W in the codomain, and also this negative V2 lives in W in the codomain. They are very easily expressed. V1 and negative V2 are very easily expressed in function of the same basis as the domain, namely V1 and V2 themselves. Therefore, we pick W1 and W2 to be the same basis as V1, V2. I remind you that in lecture 9.3, the matrix A, SL, Vj, Wi is written column-wise. Its first column being the coefficients of the linear combination expressing the image of V1 in terms of the basis of the codomain. So the image of V1, as we said, is V1 itself. We want to express V1, in order to find the first column of the associated matrix, we want to express V1 as a linear combination of the basis we have chosen of the codomain, W1 and W2. But W1, W2 we have chosen to be exactly the same as V1, V2, just because, as we notice, V1 is easily expressed in terms of the basis V1, V2. So we have chosen W1 to be V1, W2 to be V2, and we immediately see that the linear combination using these vectors as basis is the one that has 1 as a coefficient of V1 and 0 as a coefficient of V2. We don't need to do any computation. We don't need to solve any system or linear equation. We can see it just immediately. These two coefficients, 1 and 0 of the linear combination, form the first column of the associated matrix, 1, 0. The second column is computed by doing the same, except that we want to see the image of the second vector of the basis of the domain, so not V1 but V2. The image of V2 is negative V2, which expressed in terms of W1 and W2 is just as easy as before, because W1 is V1, W2 is V2. Therefore, we immediately see that the component of V1 must be 0, and the component of V2 must be -1. So this shows that the second column of the associated matrix, so these two question marks, are 0, the first, and -1, the second, and the associated matrix with respect of these two bases of the domain and codomain, Vj and again Vi, because Wi have been chosen to be Vi themselves, is this matrix here. The associated matrix is the conversion in numbers of all the informations contained. The associated matrix is the conversion in numbers of all the information contained in the homomorphism SL. So these four numbers contain everything that SL carries as information, but in order to reconstruct SL, we need the bases Vj and Wi. Therefore, it is more correct to say that the associated matrix and the choice of the two bases, all three together concur in reconstructing completely the homomorphism SL. Let's see now a numerical example. Let's take L to be the line generated by the vector 1, 2. So we are representing the line in a parametric form, providing the basis of this subspace. We have noticed that in order for SL to be an homomorphism, the axis of the axial symmetry must contain the origin. Therefore, all these axes are one-dimensional subvector spaces of R2, and they admit a basis. Being one-dimensional means that the basis will contain just one non-zero element. So in this case, let's suppose that this axis is generated by the vector 1, 2. Following the previous prescriptions, we choose V1 to be one element of the axis, so why not choosing the same generating vector of L, so 1, 2. And then we have to find a perpendicular vector to V1, and we will call it V2. Any perpendicular vector will do it, and 1 is -2, 1. We will see in future lectures when we will cover the scalar product how I came up with this vector here V2 immediately. And again we choose, as in the general example before, we choose the basis of the codomain to be exactly the same basis as the domain. So we already computed the associated matrix, which is 1, 0, 0, -1. In the numerical example, the only thing missing was finding the explicit basis of the domain and the codomain. How do we use the associated matrix to recover the homomorphism? For instance, how do we use this data to compute, say, the image of 3, 1 through the homomorphism SL? Well, in lecture 9.4, we explained the procedure. The image of 3, 1 will be a linear combination of the basis of the codomain, W1, W2, with the coefficients that we have to compute. Let's call them mu1 and mu2. And the condition that these mu1 and mu2 must satisfy are dictated by this equality. So mu1 and mu2 are the product of this column vector lambda1, lambda2 multiplied on the left by the associated matrix. How do we find lambda1, lambda2 since the associated matrix we already have? Lambda1, lambda2 are the coefficients of the linear combination that express the vector in the domain of which we want to find the image, in this case 3, 1, in function of the basis of the domain. This involves solving a system of linear equations with two unknowns, lambda 1 and lambda 2, and two equations given by each equation is associated to each of the coefficients of these two vectors. I have a two-dimensional vector on the left-hand side and a two-dimensional vector on the right-hand side. So step A, we want to express the vector 3, 1 as a linear combination of the basis of the domain. The basis of the domain was v1 equal 1, 2, and v2 was the vector negative 2, 1. Therefore, we have to solve this system of linear equations. If we expand the right-hand side, we can compute explicitly this vector and its coefficients. The first coefficient will be equal to lambda 1 minus 2 lambda 2, and the second coefficient 2 lambda 1 plus lambda 2. Here we are using the vector space structure of R2 that we defined at the beginning of the course. Multiplication by scalars and summing vectors inside Euclidean vector spaces. The quality of these two-dimensional vectors, namely 3, 1 and the vector here on the right-hand side, occurs when the coefficients of the first vector and the second vector coincide simultaneously. And this is the same as saying that the equality of 3 with this coefficient must happen at the same time as the equality of 1 with the second coefficient. And this mathematics is written in the form of system. System means that all the conditions that appear on the right of this curly bracket must happen simultaneously. So we want that at the same time 3 equals to this expression and 1 equals this expression. So we solve this system of two equations in two unknowns, and we find that lambda 1 must be equal to 1 and lambda 2 must be equal to negative 1. Therefore, since mu1, mu2 is obtained by taking this as a column vector and multiplying on the left by the associated matrix, mu1 and mu2 end up being 1 and 1, both of them. We can plug it back here in the quality describing now the image of 3, 1. So the image of 3, 1 equals mu1, which is 1, times w1 plus mu2, which is 1 again, times w2. This means w1 plus w2. And w1 and w2 have been chosen to be equal to v1 and v2. Hence, w1 is 1, 2, w2 is negative 2, 1, and the sum of them is negative 1, 3. And this is the image of the vector 3, 1.